Okay, so this lecture is about the vector form of Coulombs law. So in calculus-based physics, we deal with vectors a little more complicated than we do in algebra-based physics. So what we do in algebra-based physics is we calculate the magnitude of the force between two charges. So we draw these vertical lines to show that this means magnitude, and we say that's equal to Coulomb's constant times Q1 absolute value, Q2 absolute value divided by R squared. So if we have a negative charge, we make it positive. If we have a positive charge, we leave it positive. So these two charge values, when we multiply them together, they're going to be positive. K is positive, R is positive. So we get a positive result. And then we kind of use a vector diagram to give us an idea of what direction they're in. So the difference here is that if you wanted to find the vector directly, vector force on object charge 1 due to charge 2, you don't have to use these absolute values. You just have to use this form. So you still use K, which is a scalar, it's just a constant, and use capital Q. In the book they use, well, this is the Giancoli book. Let me see what they use for just normal. They still use Q1 and Q2. They use capital Q1, capital Q2, but really the same thing. Now these are still scalars. These are going to be charges in coulombs or microcoulombs. But the thing is, then you multiply by this little R hat 1, 2. Okay, so what the heck is that? Let's say we have a point charge here, and we have a point charge right there. And if we, let's say they're both positive, just for argument's sake, and what that means is the force is going to be in this direction. It's going to be in the same, if I were to extend this, it would go right through there. Okay, so in this case, the force is going to be pushing, one's going to go this way, and one's going to go the other way, because they're equal and opposite. Okay, and this is object. This is the charge 2. This is charge 1. So this vector is the force vector on charge 1 due to charge 2. Now this little R hat vector has the same direction. It's a position vector. This would be the position vector between the two. So we would call this R1, 2. That's the vector. So let's get some dimensions here. Let's say we have 4 meters in the x direction, and then we have 3 meters in the y direction. So we would say that the position vector between charge 2 and 1, and actually I've got my subscripts on this thing, so this should be the force of on charge 1 from charge 2. It's R21, not R12. So this, let me change that as well here. Okay, so this vector is the vector from charge 2 to charge 1. So it's just the distance vector. And that vector is going to be 4I plus 3j. So we move 4 units in the x direction and 3 units in the y direction. So that's our position vector. Now what we have here, we have R hat 2, 1. This is the unit vector. So the unit vector has the same direction as the vector, but it has a magnitude of 1, whereas this would have a magnitude of 5, because 4 squared is 16, 3 squared is 9. 16 plus 9 is 25. Take the square root. So this distance, the magnitude of this vector, so if we said the magnitude of R21 is 5. This squared plus that, take the square root. Whereas the magnitude of the unit vector is 1. So how do we get the unit vector from the vector? So it turns out that the unit vector is equal to the vector divided by the magnitude of the vector. So in this case, we said the magnitude is 5. So we take, this is basically the same as 1 over the magnitude of the vector times the vector. This gives us, this is a number, this is a vector. So we get 1 over 5 times the vector, which would be 4i plus 3j, or 4/5 I plus 3/5 j. So that is the unit vector. If we were to take this squared plus that squared, add them together, we'd get 1. So that's would confirm that the magnitude of the unit vector is 1, but that's how you calculate the unit vector. So let's take this. I want to make it smaller, so it's going to be shorter, of course. It's going to be 1/5 length. So this would be r hat 21, whereas this, the whole from here to here is r vector 21. Okay, so that's my unit vector. So if we go back to our calculation here, that's what I use. So if I want to figure out what the force vector is on charge 1 from charge 2, I take the Coulombs constant. Well, let me give you, before we do that, let's give them some values here. So I'll say Q1 is 3.0 times 10 to the minus 6 coulombs, and that's Q1, which is this charge. And then Q2 is, let's say it's 4. So they're both positive, which is what I had here, so they should repel each other. So those are Q1 and Q2. K is constant, 9 times 10 to the 9th. And R is, this R is 5. It's the magnitude. So now let's just plug these things in here. So K is 9 times 10 to the 9th Newton meters squared per Coulomb squared. I accidentally pushed the button that made that change to black. And then we have Q1, which is 3, positive 3, times 10 to the minus 6 coulombs. So it's 3 microcoulombs. You could write that as 3.0 microcoulombs. This one is 4 microcoulombs. 4 times 10 to the minus 6 coulombs, all divided by 5 meters. And then I ran out of space here, so I'm going to squish this up a bit. So there it is. And then you multiply this by the unit vector, which was 4/5 I plus 3/5 J. So what we can do is we can do this calculation of the numbers at front, which would be 9 times 10 to the 9th times 3.0 times 10 to the minus 6 times 4, 10 to the minus 6th, divided by Oh, I forgot to square that. 5 squared. Okay, 5 squared. So the numbers in front are 0.00432 times 4/5 I plus 3/5 j. So the final answer here, the force vector, we take 4. So what we'll do is we'll take 0.00432 times 4 divided by 5. So we get plus 0.00346I plus so the second part of the calculation would be 0.00432 times 3 divided by 5, which is 0.00259 j, and that would be the answer. Of course, F21 would be these, but the sign's changed. So this one's going positive x and positive y. You can see it does do what we think it should do. Whereas this one's going to be going the opposite direction, which is going to be to the left and down, which is going to be negative. Now, if this point, say this point 1, charge 1 were down here, then R21 would have a positive x and a negative y. And so that would work out as correct too. So that's how you handle it. Let's kind of review what we just did. This is what we do in algebra-based physics. This is the expression you would use if you want to do it in a vector form. Here, you're taking the positive of both of them, whether they're both positive or you just make them positive quantities. Here, you use the actual sign. So in this case, they were both positive because that's how I specified it. But if this were a negative charge, this were a positive charge, then you'd have one negative, one positive. This is the distance. It's a scalar, and it is basically it's the magnitude of the vector from here to here. It's a length. So we took 4 squared plus 3 squared, which is 25 to the square root. That's r. The unit vector from charge 2 to charge 1. So this is the tail of the vector. This is the tip of the vector. The unit vector is the vector, which is from here all the way to there, divided by the length of the vector. The unit vector has a magnitude or length of 1 unit. This is the unit vector right there. Okay, so that is how you handle it.